Hi, I'm Professor Goins. In this video, I'm going to look at solving systems of linear equations by graphing. In particular, systems of linear equations with two variables and systems where there's two equations. Okay, geometrically, here are the three situations. I can either have parallel lines, I can have lines that are exactly the same, which in particular, they are also parallel. So I've got parallel but different, parallel but the same, and then not parallel. Let's look at each case. If I have parallel lines, notice there's parallel lines and they're different. Then there's no intersection, which means there's no solution. Remember, a solution to a system of equations is an intersection point between the lines. These never intersect, hence have no solution. These two lines right here, since they completely overlap, every single point on the line is an intersection point. Every single point on this blue line touches the red line, so therefore that's an intersection point. And hence, every single point on the line would be a solution, which means there's infinitely many solutions. In this third case here, I have different slopes, which means they're not parallel. They will intersect at one point and one point only, and therefore there's one solution. So when you go through and you're solving your systems of equations, sometimes you'll get one solution, infinitely many, or no solutions. And geometrically, these are what's being represented. Let's go through and solve three systems of equations by graphing. Okay, so I've got A, B, and C. Each one of these has the form where it's a linear equation with two variables, and we have to, again, solve it by graphing. So let me go ahead and let me clean this up, and let's work through each of those three. Solution. For part A, in order to graph those lines, what I'm going to start by doing is writing them each in the form, and this is for all A, B, and C. I'm going to start by converting each one of those to the form y equals mx plus b. Remember, m is your slope, b is your y-intercept. If you're not sure how to do that, well, we'll walk through a bunch of examples here. All right, so let's start with part A equation, the first equation. We've got x minus y is equal to 2. What I want to do is I want to put this in the form mx plus b. I'll subtract x to the other side, giving me negative y is negative x plus 2. And then to isolate y, I'll divide by negative 1. And remember, when I divide this side by negative 1, every term has to get divided by negative 1, giving me x minus 2. This right here then would be the first equation of this system. Same thing with the second equation. X minus y is equal to negative 1. Let's do this one slightly different just so you see a variation. I've got negative y. I'd like to end up with a positive y. So therefore, let's add y to the other side, giving me x is equal to y minus 1. And then I can add 1 over here, giving x plus 1 is equal to y. And I've got y isolated. Therefore, I've got my system of equations in the form for which I can graph it. And let's get a rough sketch of what this graph would look like. See if I can do it down here, if that would be on the board. The graph of y equals x minus 2 has y-intercept negative 2 and slope 1. Therefore, it would look roughly like this. So this would be y is equal to x minus 2. Notice the y-intercept is down here at negative 2. And then I'll graph y is x plus 1, which has y-intercept of positive 1 and slope 1, which gives me this line right here. This is equal to y is x plus 1. Now those are parallel lines and they're different lines, so therefore there's no intersection, which I'll abbreviate as INT. There's no intersection, therefore this system has no solutions. Okay. Part B. X minus y is 2, so let's start with that. X minus y is equal to 2. Again, what I could do is I could add y and then subtract 2, giving me x minus 2 is equal to y. That's the first equation that I'll graph in this next system. And then I've got x plus y is 4. All I have to do to isolate y is subtract x to the other side, giving me y is equal to negative x plus 4, and this would be the second equation that I have to graph, or the second function that I have to graph. All right, let's take a look at that picture. Okay, this time let's put some tick marks in here for our graph. I'll go 5 units in each direction. So I've got 1, 2, 3, 4, 5. Y equals x minus 2. Once again, that has the y-intercept of negative 2 and slope 1. Okay, so this is y is equal to x minus 2. And then negative x plus 4, this would have a y-intercept of 4 and slope negative 1. That's going to go through 1, 2, 3. It's going to go through this point here. And then if it has slope negative 1, down 1 over 1, or equivalently down 4 over 4, which means it's going to pass through this point here. And this is y equals negative x plus 4. And we can see that there is, in fact, an intersection point. And this is why when you graph these, you want to try to be somewhat careful. The more accurate you graph these, the more accurately you can pick off this point. If I drew this really sloppy, I might see that there's an intersection point, but it might be kind of hard to identify what exactly it is. So make sure you try to draw these fairly carefully. If I look at this intersection point here, it looks like we did a decent enough job where it's over 1, 2, 3, and then so it's approximately over 3 and then up 1. So we can make the guess that it is over 3 and then up 1 as my solution. We can check that in the original system. Remember, the original system is here. X being 3, y is 1. If I take 3 minus 1, that's 2. 2 equals 2. That checks out. Down here, 3 plus 1 is 4. Over here, I've got 4, so that checks out as well. Therefore, this is, in fact, the solution to that system. All right, finally, let's look at the graph for part C. Same idea, I'm going to isolate y in each case. For this first equation here, start with 2x plus y is equal to 3, and all I have to do is subtract 2x to the other side, giving me y is equal to negative 2x plus 3. And this will be the first line that we graph. And then I've got x minus 2y is equal to minus 1. To isolate y, what I'll do is I'll add 2y, and then I'll add 1. That would give me x plus 1 is equal to 2y. But now I have to divide by 2. That would give me 1/2 x plus 1/2 is equal to y. Remember, if I divide this by 2, I have to divide this whole side by 2. And if I divide this whole side by 2, I have to divide each term by 2, giving me x divided by 2, or equivalently 1/2 x, 1 divided by 2 being 1/2. This would be the second line that we have to graph. All right, same thing as we did over here. Let's do a coordinate system and let's put some tick marks in it so we can try to do this somewhat accurately. Let's try the same thing. I think 5 units in each direction should be plenty. Okay. The first line we have is a y-intercept of 3. And then a slope of -2. That means, remember, slope is rise over run, so I think of that as -2 over 1, meaning that from this point, I'm going to go down 2 units and then over 1, putting me right here and giving me this line. Okay, this is the graph of -2x plus 3. Okay. Now for the second one, I've got 1/2 x plus 1/2. The slope, or I'm sorry, the y-intercept is 1/2, so we'll go between 0 and 1, and we'll just sort of ballpark it right there in the middle. And then slope is 1/2, which means I would go up 1 unit and over 2, meaning I would go up 1 to say 1.5, and then over 2, which would put me to here, and then I'll draw the line through those two. Okay, so this is y equals 1/2 x plus 1/2. We see that there's an intersection point, so we know that there's a solution. And now we just hope that we graphed it accurately enough that we can pick off what that exact location would be. And this intersection point here looks like it's approximately over 1, up 1. Therefore, we'll make a guess that it's going to be the coordinates 1, 1. Now let's check it in the original system and see if that solution works in both equations. If I plug 1 in for x, 1 in for y, 2 times 1 is 2, 2 plus 1 is 3, equals 3, that checks out. Over here, x minus 2 times 1 would be 1 minus 2, which is -1, equals -1, that checks out as well. All right, so let's recap what we did. If I want to solve a system of equations, what I'm going to do, or solve a system of equations by graphing, I'm going to take each of these equations, put it in the form y equals mx plus b, graph the pair of lines, so graph each line independently, and then I'll see if there's an intersection point. If there's an intersection point, then that point, so this point here, the intersection point, this point here, the intersection point, would be the solution to the system. Sometimes there will be no solutions, and that just is represented with parallel lines. The last case, which we didn't have an example of, but if the lines happen to overlap, meaning they're the same graph, like for example, let's say this black line here, what if the red line was exactly that same graph? Then there would be infinitely many solutions.